As our third session in this project, we are going to investigate the lift, drag, and moment of a NACA 0015 airfoil. Just like the previous projects, we drag a fluid flow block into the blank space and double-click on the geometry. Now, for the first step, we need to create the outline points of our airfoil. To do that, we click on Create and then select Point. On the low left side of the software window, in front of Type and Definition, make sure that Construction Point and From Coordinate files are selected. After that, on the coordinate files, we click on the None and select the files where the coordinates of the airfoil points are saved. It should only be pointed out that the data that exists inside the text file you are importing to the Design Builder software should look something like this, and it should have titles just like the shown table, which are highlighted with a green color. After importing the coordinates of our airfoil points, we click on Generate button. Now that we have imported the outline points of our airfoil, it's time to import the outline curve of our airfoil too. To do that, we click on Concept and select 3D Curve. Just like what we did to import points of our airfoil, we do the same thing here to import the curve too. Now, if we rotate the end of our airfoil and zoom a little bit in, we can see that the end of our airfoil is open. To close this open end, we need to create a point at the end and then connect it with the two other points. After selecting the point from the Create tab, this time in front of the Definition section, we need to select the manual input and then enter the coordinates of our point, as you will see in the next slides. Now that we've created our ending point, it's time to connect this point with the other 2 points using the line from points command. Now that we've created 2 separate lines at the end of our airfoil, we need to merge these 2 lines with the main curves of our airfoil. To do that, we click on Tools and then select the command Merge. Now using this command, we select the upper curve and select the upper line that we've created at the end of our airfoil. After that, we click on Apply and then click on Generate so that the software will make these 2 lines a united line. We also follow the same steps for the bottom lines. Now that we have created the outline of our airfoil, it's time to create the outline of our domain. To do that, we need to create 6 points that we are going to enter their coordinates separately in the next slides. Now, as you can see in this slide, we have created the points that we needed in order to make the outline of our domain. Now it's time to connect these points. To do that, we click on Concept and then select the Line from Points command. Here we need to select our points pair by pair. Since in this project we are going to use a structured mesh for our domain, we need to separate our domain into multiple parts. To do that, we click on Concept and then select Line from Points command again. Please make sure that you select the same exact points in order to avoid any other problems in the next steps. Now that we have divided our domain into multiple parts, it's time to turn these parts into surfaces. To do that, we click on Concept and then select Surface from Edges. After that, we click on each of these edges, as you can see. Now, just like the previous session, if you expand the part section under the tree outline, you can see that a line body along with 6 other surface body exist here. Now we right click on the right line body and suppress it since we do not need it anymore. And we select all the 6 surfaces and right click on it and select Form New Part since we want to introduce this geometry to the ANSYS meshing software as a whole body. And of course, the final step is to change the type of this body from solid to fluid. After that, we click on Save button to save our project and close the Design Modeler software. Now in the workbench environment, we double click on Mesh so that we open the ANSYS meshing software. Now under the outline section, you can see that all of these 6 surface bodies are counted as one part. Now in order to define the number of mesh cells over different edges, we right click on Mesh and then go over Insert and select Sizing. In order to make our selection easier, we click on Edge button and then select our desired edges. After selecting our desired edges and then clicking on Apply in front of the geometry, we change the type from element size to number of divisions. In front of the number of divisions section, we enter the value of 100 so that we can have 100 mesh cells over these selected edges, and we change the behavior type from soft to hard. Now in order to create boundary layer mesh, we enable the bias type and we select the format where we have a smaller mesh near our airfoil. We also enter the value of bias factor equal to 20, meaning that our biggest mesh cell has a width of 20 times bigger than our smallest mesh. Now if you pay attention to the direction of mesh cells over some of these edges, you can see that the direction of mesh cells over these edges are not correct. To correct the direction, you can select these edges and then enable the reverse bias option. Now to assign the number of mesh cells over the other edges, we again right click on Mesh and then go over Insert and select Sizing. Now just like the previous edges, after selecting these edges, we click on Apply in front of the geometry and we change the type from element size to number of division. And we enter the value of number of divisions of mesh cells over these edges to be equal to 150. After that, we change the behavior from soft to hard. And for the rest of the edges, we do the same thing and we select edge sizing for these edges and we enter the value of number of divisions of mesh cells over these edges to be equal to 25. We also enable the face meshing option. To do that, we right click on Mesh and then go over Insert and select Face Meshing. Now in order to select all of the surfaces of your geometry, you just can simply right click on an open space and then click on Select All. If you do that, you can see that only 2 surfaces are shown to be green, meaning that they are selected. But if you rotate your geometry a little bit, you will see that the rest of the surfaces are selected and are green on the other side of your geometry, meaning that all of the surfaces are selected. Now that we have adjusted all the settings for our geometry, it's time to create the mesh. To do that, we right click on Mesh and click on Generate Mesh button. Now after creating mesh for our geometry, it's time to create name for the boundaries of our geometry. To do that, while holding down the Control key, we click on the left edges of our geometry and right click on them and select Create Name Selection. And we set the name of this boundary to be the inlet boundary. We do the same thing for the right edge, and we set the name of this boundary to be the outlet boundary. We name the top and bottom edges of our geometry to be symmetry boundaries. And for the final part, we select the outer edges of our airfoil to be our roll boundary. We also select all the faces of our geometry and we set the name of flow for them. After that, we exit the ANSYS meshing software and launch the Fluent software. In the opened window for the Fluent software, we enable the double precision option, and in front of the solver processes, we enter the maximum number of our CPU cores. Now in this project, our solver type is set to be pressure based since we are dealing with incompressible flows. Also, you can see here that we have selected the planar 2D space, and as for the time study, we have selected the steady time study since we didn't want our results to be a function of time. In this project, we are going to use the turbulent models for solving our fluid flow. Among the existing model, for normal system that we have, it is more common to use K epsilon and K omega models. There are a lot of differences between these two, but the most important difference between them is that how they model the velocity profile in the boundary layer. In the K epsilon model, the velocity profile in the boundary layer is assumed to have a logarithmic shape. However, in the assumption of K omega model, it is stated that we should take the mesh cells as small as possible so that the assumption of linear velocity profile in each of these small cells can become valid. But now, using the SST-K omega model, we can benefit the advantages of both models, meaning that we can solve our fluid flow problem faster since we do not need a small mesh cells in our whole domain, and that we can obtain more exact results near our wall boundaries. In the material section, we do not need to make any changes and we'll let the air material to be the main material of our problem. In the cell zone conditions section, just like the previous section, we do not need to make any changes since we didn't add any material. As you can see in this window, we'll let the material name to be the default material, which is the air material. Now if you click on the inlet boundary and then click on edit button, in the appeared window in front of the velocity magnitude, we enter the value of 17 meter per second. Now about the value of turbulent intensity, it should be pointed out that this value should be extracted from the experimental work and from the articles. But now in this problem, we set the value of turbulent intensity to 0.1, which is the turbulent intensity of the airflow inside wind tunnels. Also, using this value for turbulent intensity have the benefit of increasing the speed of our convergence. After clicking on outlet boundary and then clicking on edit button in the appeared window in front of the gauge pressure, make sure that you have entered the value of 0, and in front of the backflow turbulent intensity we again enter the value of 0.1. Now, just as we explained in the previous two sessions, in this problem we exploit the simplest scheme for our pressure velocity coupling too. It should only point it out that we changed the spatial discretization related to turbulent kinetic energy and specific dissipation rate from first order upwind to second order upwind. In the problems where we have jumps in our mesial sizes, and by jumps look at the corners of this geometry, you can easily see the changes of mesial sizes at these places. Now, if these jumps are too big, we are going to face problems in the way of convergence process. In order to avoid these problems, we have to manipulate the under-relaxation factors. By changing the under-relaxation factors for parameters like pressure, momentum, etc., we first let the mesials to obtain a value near to the exact value. And then by changing these factors to the default factors, we can make sure that the convergence will occur without any problems. Just like the previous session, we uncheck the check convergence option for different parameters so that the software will solve the fluid flow problem till the last iteration. In the initialization section, we select the standard format, and under the compute from, we select the inlet boundary, and then we click on initialize button. Under the number of iteration, we enter the value of 700, and then we click on calculate button. Now, in order to calculate the pressure coefficient, we first need to correct the value of velocity in the reference values. To correct the value of velocity, we simply can either change the value here or just by clicking on compute from and then selecting the inlet boundary, the value of velocity will be corrected itself automatically. Now, after correcting the value of velocity, we expand the plot and double click on XY plots. In the appeared window under the y-axis function, we make sure that the pressure is selected, and underneath it we select the pressure coefficient. Also under the surfaces section, we select vol, which represents the airfoil boundary, and then click on Save or Plot button. Now, if you compare this diagram with the diagram that is extracted from the article and presented in the next slide, you can understand that our results are valid. It should only be pointed out that this diagram shows the minus values of pressure coefficient over the position. Now, as you can see in the formulation for two parameters of drag and lift coefficient, you can see that the value of surface plays an important role in correctly calculating these two coefficients. Now, in the reference value section, you can see that the area has the value of 1, which is correct here because the chord length or the main length of our airfoil was also equal to 1. In order to calculate the values for lift and drag force and coefficient, we expand the report section and double click on the forces button. Under the options section, we select forces, and under the direction vector, we enter the value of x to be equal to 1 since we want to calculate the drag force and coefficient first, and under the vol zone section, we select the vol boundary and then click on print button. In the console tab, you can see the values of pressure drag force, viscous drag force, and the total drag force, which is almost equal to 2.63 newtons. You can also see the drag coefficient, which is almost equal to 0.015. Now, in order to calculate the lift force, since this force is applied in the y direction under the direction vector, we enter the value of y to be equal to 1 and we set the value of x to 0. After that, we click on Print button. Now in the console tab, just like the slide related to the drag force, you can see the values of the lift force and lift coefficient, which has the value of almost 0 since our airfoil is symmetric, and the angle of attack was also equal to 0. You also can view this symmetry in the graphics section by extracting, for example, the pressure contour. To extract the contours, we expand the graphics section and we right click on contours and then select new. In the appeared window under the contours of section, we select the pressure and we click on save or display button. Now in this contour you can easily see the values of pressure in the upper section and the lower section of our geometry is completely symmetric, and that is the reason why we have the lift force value almost equal to 0.
To benefit from Mr. CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.